So let's start with the productive failure 23. And this one, it shows a boy standing on a skating board holding a bowling ball. And initially he's not moving, right? He's just holding that. But when he throws the ball forward, he moves backward. Now the question is, how would you explain this event? Okay, so what you guys came up with?
Well, that if, because as he throws the ball, he's pushing into the ball, as he throws it away,
Mm-hmm.
throws it forward, and then that same force gets carried on the other side, the negative side. So it's equivalent. So that's he moves at the same speed. He's moving away from the ball, I guess.
Yeah. And what about you?
So the force that he's using to push the ball, it's like force times the weight, the mass of the ball. So the same force in Newton is reversed. So he's gonna move backward. Now, obviously not as far as the ball because the ball is much lighter than him. But yeah, that's it.
So some kind of
Reaction.
action and reaction
Like
kind of thing?
Third law. Newton's third law.
Newton's third law. Okay, very good. So let's now discuss the other one. This one. So, which one? What will be your answer? Here, what is happening is, what is behind the idea of having a seat belt or airbag in a car, and how you explain that? You know.
Or it delays the time.
Delaying the time, it delays the time of being, you know,
And the
impact.
effects of the shorter the time, the
Mhm.
more force, the longer the time, the less force you're gonna get. So that's why the seatbelt comes into play, delays the time for the impact, plus the airbag also adds to that time as well.
Okay, very good, excellent. So let's let's talk about the new concepts today. So what we're going to learn today is so far, we start learning about units, right? Measurements and things like that, the importance of that. The second thing that we learned was physical quantities. And we learned there are two basically physical quantities that, you know, we can mathematically describe. One is a scalar, that is just a magnitude, and the other one is what? Vector, right? Good. The other content that we covered was linear motion. And in physics, we want to describe things, and one way to describe motion is by keeping track of your position with time. So we did learn about you know, rate of change. Rate of change we call what? Rate of change in position. What is that called?
Delta X.
The what?
Delta X.
The instantaneous velocity.
Velocity, right? You know, rate of change in distance or position,
No,
you
that's
know,
the
is
distance.
That's the,
Velocity has time now.
say the rate of change between distance and time, is that what you said?
yeah.
Yeah, that's
How would
velocity.
the time,
Yeah, that's
Yeah.
velocity.
Or displacement, right?
Mhm.
It is a vector, right? Speed would be, you know, the distance traveled divided by the time, okay? Then this is when we have a uniform motion, so that means the velocity is not changing. Acceleration would be what?
Constant.
Constant, zero, right? Would be zero. If the velocity is not changing, right? Acceleration is zero, right? Now, if velocity changes, that means we have an acceleration. And velocity can change by increasing or it can change by decreasing, right? Then we discussed Newton's laws, right? The first law is that, an object, if there is no force applied to it, it's not going to change its situation of rest. It's not, right? If it's at rest, it's not going to change that. Or if it's at a constant speed, it's not going to change either, right? It's going to continuously run that way. But now let me ask you one thing about that, if a mosquito, right? A mosquito is flying at 10 meters per second and hit me, is that going to cause anything? No, right? The worst thing it can cause is that I'm allergic to it, if it bites me, I'm going to have a little bump, right? But what if a car hits me at 10 meters per second? It's the same speed, but what's happening there?
The mass is
Mass is
different.
bigger.
The mass is bigger. So that tells me there must be some physical quantity that is going to relate the mass and the speed, right? Because it causes some sort of effect. We know, there is a difference between the mosquito and the car. Right? So with that, there is this thing that we call linear momentum. Okay. And we define linear momentum by the letter P, and it's going to be m times the velocity, okay? So now there is this other quantity. We have force. Force is also a physical quantity, right? But now we have this other one that is called linear momentum, all right? So let's think about now that what about, is linear momentum a vector or a scalar? What do you guys think? Is mass a vector?
No, but velocity is.
But velocity is. So velocity is a vector. What about momentum? Is momentum going to be a vector?
But that's
Yeah.
the force of time, right?
Momentum is a vector?
That's a vector.
Is it the moment? That's mass? What is it?
This is mass.
Okay.
Mass
So-
times a vector.
So P is a vector.
So P is a vector, right?
Yeah.
Is that okay?
Yeah.
All right. Remember, when you guys were doing the vector simulations, right? You could multiply, right, a vector by 2, and the vector would be not a vector, but 2 times, the magnitude would be 2 times, right? So here, this is the same, okay? So now, if there is a change in velocity, so like a delta V, right? Delta V times m, I'm going to have a change on momentum, right? Delta V is mass. So mass times the change in velocity. So how's that? Let's say I have an object A. Object A here. Object A. Object A has mass 1. Okay? And object B has mass 2. All right? Now, object A is at velocity, initial velocity, VA0. Object B is at initial velocity, VB0, right? Now, they can collide, right? And what do you think is going to happen? Is the velocity going to be the same, or is it going to change, or what do you think?
What's your question exactly?
I have two objects.
Yeah.
Object A,
Without that
mass 1 with a velocity
have the same mass?
VA0, and object B, mass 2 with a velocity VB0.
Yeah.
Okay? Now, if they collide, what do you think is going to happen?
Well, we need to know what's the difference. I mean, they're gonna move, yeah, they're gonna,
Yeah, they're gonna, is gonna be a velocity, the
Yeah.
same velocity, or is
No,
gonna
it's
be
gonna
different?
change. It's gonna
Huh?
change.
It might change,
they're
right?
gonna change the velocity.
So let's say, what is the velocity final, and then VB final, right? Now, here, let's look here again. If I divide these two here on a specific time, this change is done at a specific time, at delta t. So I need to divide this here by delta t. I divide this here by delta t. Okay? So have here momentum. Momentum has changed at a certain time, right? It's changing at a rate, right? If momentum is changing at a rate, delta v, delta t is equal to what?
The average
Average,
rate of change,
average of what?
velocity.
Delta v divided by delta t.
Oh.
What is delta x divided by delta t? What is that? Is that
So that's velocity, so that's acceleration.
That's velocity, right?
Velocity, that's
And this here is acceleration. Excellent. This here is acceleration. Average acceleration. Now, mass times acceleration is equal to what?
Force.
Force. So force is equal delta P divided by delta T, and this is equal to ma. All right? You see that? We start here from linear momentum. Linear momentum is mv, right? If V is changing, right, the momentum is going to be changing. Now, if the delta V is changing at the rate of time, now we see that force is equal to the rate of change of momentum over time is equal to force. Now, if I multiply these two, F times delta T is going to be equal to delta P, so the change in momentum is equal to the force times delta T. We call this impulse. Okay? This is what we call impulse. And this is called the impulse momentum theorem. The idea that impulse is equal to the change in momentum. Okay? That is the impulse momentum theorem. Okay? Now, when we had our experiment, the rocket, you guys remember the paper rocket? The mass of the paper rocket is 13.11 grams. We measure the range. You guys remember we measured the range? So we were able to calculate the initial velocity, right? When the rocket is being launched, what was the initial velocity? The initial velocity was, let's see, how much was that? 15 meters per second. 15 meters per second. So, the initial velocity is actually the velocity that, the rocket is leaving the launcher, right? But what was the velocity before the rocket launched? Zero, right? So delta V is what? Is the initial velocity that we calculated minus zero, right? So delta V is 15 meters per second. The mass is 13.11 grams.
Wouldn't that be final velocity?
Yeah, well, it's not really final because, you know,
Velocity doesn't change. Velocity doesn't change in X, but it does change in Y.
it changes on the one.
Mm.
Yeah. But here what's happening is, you know, it goes up. Remember it goes up like this
Yeah.
and then falls, right? So you have all this,
Oh.
this thing here, right?
Yeah.
And this velocity changes, right?
Mhm.
As it goes, right? Now, this initial velocity here, it's kind of confusing because what I'm comparing here, I'm just focusing on before and after it was launched, right?
Oh,
Before
okay.
it was launched, the velocity
Zero.
was zero because it was not moving.
Mhm.
So at this moment here, the impulse that it received, that's what I want to focus on, is the mass times delta V, right?
Mhm.
The change in impulse.
So it will be like 13.11.
13.11
times.
times 15, right?
Which is that the final or the initial?
That is this when it was
Oh,
launched.
as soon as okay,
Yeah.
okay.
I can call this, let's call this final. If we just focus on this.
Uh-huh.
We call initial velocity
Oh,
of the,
okay, I
of
understand.
the,
I understand now. Yeah.
you understand now?
Mm.
Okay, so I got these two values
So,
here.
yeah. So that velocity would be as soon as you step on the bottle.
Yes,
Oh, okay, okay.
yeah. Step on the bottom and this thing is
Mm.
launching, it's leaving the
So
launcher,
wait,
right?
I'm sorry. The 15 meters per second, which one is it?
This is the velocity that you calculated, you know,
So
based on
is
the
it the
range.
VF or the V final or V initial?
This is the V final when you think about the
Okay.
launcher.
So
you
the
know,
V initial is, so the VO is then 0 meter per second.
Yeah, I understand. So before you step on the bottle, the initial velocity was zero because it was
Yeah.
moving. As soon as you put your feet on the bottle, that was 50 meters per second because now it's moving, right?
Okay.
That's what we calculated.
So
So
it-
in terms of the velocity, okay, so before you put your foot on the bottle, that's,
So yeah, the initial
that's the
velocity
initial
was zero.
velocity. That's initial velocity. And when initial velocity was zero, final velocity was
50
15
meters per
meters per
second.
second. right?
Exactly,
But, so that what I'm saying is that you put V0.
I know, yeah. I'm
Yeah.
gonna put V
So
five.
that's what
okay?
confused me.
Because we are focusing only.
V0 is 0.
We are only focusing on the impulse,
Yeah.
Mhm.
okay? It is the V0 when we consider the whole trajectory
Oh, yeah.
of the, you know, of the
Yeah.
projectile, right? Of the, you know, rocket
Yeah.
going through.
When you would consider
Yeah.
that the trajectory,
Yeah.
that will be the big final will be the initial.
The initial
Yeah.
of the,
And then the final, once it reaches maximum range, that'll be the
Right.
final velocity.
My
The
goal
trajectory.
now here is to figure out what is the force that the rocket,
Mm.
you know, had in order to, you know, to leave the launcher, right?
Mm.
So I'm gonna leave this for you to calculate that now. So if I have M and I have this V final, that is basically the change in velocity, right? I can calculate the momentum here, right? The change in momentum. That means M delta V, right? But that divided by the time is gonna be the force. So I can estimate the force. Now, how long you think was the step on the bottom? Because that's the delta T, right?
Fraction of a second.
Yeah, a fraction of a second. But can you come up with, you know, some figure? It's 1 second?
No, less than a second.
Less than a second, right?
From when your foot touched the bottle,
It's in,
like
Huh?
the distance from like when you touch the
Instantaneous
bottle
almost?
and
Yes, but if you try to figure out how much, what would be your estimate? 1 second, half a second,
like a tenth of a second.
tenth of a
10 second.
maybe.
I estimate
I
like
mean,
30,
you could
30
calculate
seconds.
it. You
Point,
could-
0.3 seconds, right?
Yeah.
It's not even, 1 second, right? So if you estimate to 0.3 seconds, you can calculate the force, all right? I'm gonna let you
I mean,
guys do that.
You could get the actual if you measure the distance, from the height of the bottle, right? That'll be the distance. And then, I don't know, what else would you need? But you could, right?
Yeah, that's kind of difficult, right? Because it's like this, right? How long
Yeah, and
that
also
takes,
like
yeah.
not every try what you put in the same force.
Exactly,
Yeah,
it
so-
varies a little bit. So, but this is an estimate, right?
Yeah.
So you guys can figure that out now. What would be the force in newtons, right? You multiply 13 times 15 and you divide by 0.3 seconds. Now, remember, you need to use the correct units here, right? It's 13 grams, you need to convert that into kilograms. Did you come up with the value? How much?
For the force,
Yeah, for the force.
if I did the math correctly, I hope I did 0.6555.
165 newtons, right?
Yeah.
Okay.
So which one, what is it?
So what we did is we convert this here 13 grams into kilograms.
Yeah, so what I did was multiply 0.01311 by the 15
Okay, so that's 19 something? Yeah,
to get the
0.19.
momentum, and then divided that by the 0.3
Oh,
for the force.
What'd you get?
Did I do it correct?
okay.
Okay, good, all right. So now, let's talk about, Newton's third law, right? So the ball, this object is going to hit the object B, right? Let's say object B is here, not moving, and then B is gonna hit that, right? So it's like, F of A in B is gonna be equal to what?
The velocity of A.
Yeah, you're gonna be to the opposite force, right? It's like gonna be an action and reaction, right? It's gonna hit that, and the other one is gonna impact a force on A, right? Now, so if we think about the momentum of A, what is the momentum of A? Like, momentum of A. So, I have the initial velocity, right? M1 is going to be the VA initial minus VA final. Okay? That is the change in momentum. It's gonna change, right? So what is the change of momentum of A? Well, A with mass 1 has initial velocity VA0. It's gonna hit B, right? And the velocity is gonna change. Is that okay? So what is the momentum in A? It's gonna be M1. The change in momentum in A is gonna be M1 times the difference between the two velocities, right? Now, what is the momentum on B? It's going to be M2 and B0 minus BF. Is that okay? So let me erase this here. Give me more space. Now, if I divide this by the time here, right? If I divide this momentum change, I divide by the time. I'm going to have M1, VA0, VAF, divide by the time. And what is that? That is the same as M1A, and that is the force of A on B, right? The force of A on B. Now, what is the force of B on A? Force of B on A is going to be M2, M B0 minus BF divided by, and that is M2 A F B A. Okay? Now, if I take this and apply here, see? FAB is equal to negative FBA. If I apply this there, I'm going to then have M1 VA0 minus VAF divided by T equals minus M2 VB0 minus VBF divided by T. Okay? So I'm going to write this now here. So what's happening? Time can cancel each other, right? Because this time is the same as that one. I multiply T on both sides. So what is that I'm going to have? I'm going to have here M1 times VA0, M1 times VA0 minus M1 times VAF equals to M2 VB0 minus M2 VBF, and you have this negative here, right, in front of that, right? You have this negative. Now, with the negative, if this is negative, I can move this to the other side. It's going to be M1 VA0 plus M2 VB0 is going to be equal to, this guy is going to change. Negative with negative is positive. And this guy goes to the other side, it's going to be also positive. So I'm going to have now M1 AF plus M2 BF. So this here is very important. And what is this telling me? Can you guys look at this formula? M1, right? The momentum of object A initially plus the mass of B with its velocity, that is the momentum of B initially, is going to be equal to what?
The force.
No, mv.
Oh.
This is the momentum, right? The momentum of what? Of A final
Oh.
plus the momentum of B final. So what is this formula telling us? It's telling us the initial momentum of the system is going to be equal to the final momentum of the system. What is the implication of that when we do an experiment, for instance? I have a car, right? Let's say the car is floating on the track. Because the track has air, there's going to be no friction, okay? Now, I have another car coming at a certain speed, at a constant speed, with the same mass. What do you think is going to happen?
Their momentum is going to be the same.
It's going to transfer that momentum over to the second one and stay constant with that one.
So, good. I think you got that. Because what is the momentum of the second object? The second object is not moving, right?
Right.
So what is that momentum?
Zero.
Zero. So I have this momentum of the first object going towards
The second
object
one
B,
is zero.
and then what's going to happen to the final here, right? So,
Right. So once object A hits object B, that momentum, that object A, the initial velocity or initial momentum will transfer over to object B. So does that mean object A, the final velocity will be zero, or will it have a chance to move back and become negative? That's what I'm thinking.
you're in the right track, yes.
Well, if okay, so assuming the momentum of mass 2 is 0, and
It's zero because velocity is zero, it's not
Yeah.
moving, right?
So
So this one here is moving, this one is not moving.
So that means that, yeah, like the momentum of mass 1 would transfer over to mass 2, and it's going to be equal.
If the masses are equal, right? So this is the general formula. The general formula is saying the initial momentum is going to be equal to the final, right? That's clear. Now, if the mass is equal, right?
The momentum gonna
Mass
be
is
the same.
equal. So what's going to happen? I can cancel all the masses, right?
Yeah.
There's an equation on both sides. So I'm going to have VA0 plus VB0 equals to VA final plus VB final, right? Now, if this one here is 0, so what happens?
That means that the momentum of the mass A like the initial momentum of mass, the first mass is going to be the same as the final. Right?
Yeah, it's going to just transfer it to
Yeah,
the
it's gonna be
second
the same
one,
thing.
right?
Yeah.
So you guys are going to be able today to do that experiment, okay? You're going to have a car sitting on the track, and another one comes, the same mass,
Isn't-
exactly the same, and then you're going to be able to see what's happening there, all right?
Isn't that like that little toy has like 4 balls like hanging, and you swing one
Oh,
against the
yeah,
other,
yeah,
and
exactly.
then like
It transfers.
it transfers.
Transfer momentum to the next one, all right? Excellent, very
They don't
good.
move. In the middle, they don't move.
Yeah, isn't it because like they're so close together that the transfer is instantaneous, so it just shoots it over to the last one and goes back?
Yeah. So we're going to stop here now. We're going to the experiments, and then, you know, we go from there. Okay? Let's see if I have another thing to cover here. Yeah, I think this is it for today.